Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, Jascha. It's my pleasure to introduce Dr. Nikolai Gabic from Imperial College in London, and he'll present us his work in the area of noise-robust blind system identification and subband equalization of room transfer functions with applications to speech dereverberation. So, without too long introduction, Nikolai, you have the floor.
Thank you, Ivan. So, good morning, everyone. Thanks for coming along, and special thank to Ivan for inviting me over here. It's a great honor to give a talk at Microsoft Research. So as you see, it's quite a long title, so it's almost like the conclusion of the talk in the, in the title. So I guess many of you are familiar, but I have this sort of, for completeness, the reverberation issue and reverberation is that you have a situation with a talker at some distance from a microphone, where you get often, hopefully you get a direct path sound and some reflections which are somewhat delayed or attenuated versions of this direct path sound. And this causes a lot of trouble in the hands-free telephony and sound reproduction. And I say that it can have adverse effects because actually some situations it's good to have reverberation, like in music, for example, people like it. So my talk will be generally on two related, interlinked but separate blocks. One is adaptive system identification and one is on equalization. So I'll start with a quick introduction of the problem, formulating it, a few classes of the reverberation methods that I believe you can split existing methods into, and then the two main bits of system identification and equalization. So this is, I guess, familiar to many of you who worked with this. You have a speech signal S of n produced in a reverberant room, and often you model the room acoustics as an FIR filter, and the observed signal is a convolution between this FIR filter of the room impulse response and the speech signal plus some additive noise. And the aim of Dereverberation is to find some kind of estimate of the speech signal S of n, possibly delayed or scaled version of it, using the observations X only. So this is known, I guess, as a blind problem because we only have X and none of the other signals available generally. So I believe, at least from my thesis work, that you can divide the current existing dereverberation algorithms into three large classes. One is beamforming, where you have some kind of array of microphones and you try and form a beam towards your desired speaker, the source, and exclude any other interfering sources. And this is exclusive to multiple microphones. Then you have some speech enhancement methods where often you have a model of your speech signal, perhaps based on the speech production model of humans. And you try to process your reverberant observation so that it better fits this speech model that you have. Alternatively, you can also have a model of the room impulse response, which has occurred in some kind of spectral subtraction algorithms for the reverberation. And finally, you have this, the most notorious bit probably is the blind system identification and equalization type of methods, where you try to explicitly estimate the room impulse responses and design some equalization filters based on these estimates so that you can remove the effects of reverberation. And the bits I'm going to talk about fall into this last category. So this is the blind system identification issue, is to try and estimate your impulse responses H using only the observed signals X. The rest of it is sort of in the dark. So many of the algorithms which exist for this, the multi-channel system identification algorithms, are based on this cross-relation between two microphones. So you have basically that the observation of the first microphone convolved with the impulse response of the second microphone is the same as the observation of the second microphone convolved with the impulse response of the first microphone. And using this, you can form some system of equations which give you the opportunity to find the solution for H which is actually a scaled solution of H, by finding the eigenvectors corresponding to the smallest eigenvalues of R, which is a correlation matrix. And this works provided that you have that the channels are significantly different, or you have no common zeros between the room transfer functions, and that your excitation signal contains large enough spectral variety so that you can get this. One step further is, if you take this cross-relation, you can actually formulate an error signal which is extended to any number of channels by just taking various combinations of these channels. And you can use some kind of an adaptive filter to minimize this error. The good thing with an adaptive filter is that, in theory at least, it's able to track some changes in the system, which occurs quite often with room impulse responses. As you move around, the room impulse response changes, for example. So you can have this cost function based on the errors of all the combinations of channels, and there's a few different implementations, mainly by Huang and Benesti, which came out both in time domain and the frequency domain, and in particular there's the normalized multi-channel frequency domain LMS, which is quite an efficient version of these algorithms. And before I move on, I'll just introduce briefly this normalized projection misalignment, which is often used for measuring the misalignment between your estimated channel and your true channel. And the projection bit actually helps avoiding any dependence on the scaling factor which occurs with these algorithms. So that's the bit. So now if you look at a quite ideal example with this with the frequency domain adaptive algorithm, you have some 3 randomly generated channels, fairly short, 32 taps. Input is white Gaussian noise, and there's no additive noise. So
what means randomly generated channels?
It just means you just have some random taps that you generate. So it's not room acoustic.
The impulse response is random.
The impulse response, yeah, exactly. So yeah, so it's quite ideal conditions for the algorithm, and as you see, it works well, both in terms of minimizing the error, where you have here you have the cost function on the y-axis and the number of iterations on the x, and here is the projection misalignment versus the iterations. So that's fine. However, when you try and have some additive noise, for example, white noise, the problem becomes that the cross-relation doesn't hold anymore. So your cross-relation error actually consists of 2 terms. One is the original desired cross-relation error, which is the good bit which we want, but there's also a component here which is includes the noise and the channel estimates. And trying to minimize these 2 components together kind of messes up things a bit. And you can see here an example of what happens. The adaptive filters start to have this strange behavior that you start getting down, converge towards the right solution, and then they misconverge into something else. And this seems to be unavoidable. So if you just try and have a smaller step size, the only thing that changes is this point of misconvergence, that it moves a bit further later on. And the other interesting point is that this is at 40 dB SNR, which is pretty high SNR. You still get this effect. So even very, very small amounts of noise disrupt this algorithm. And the question is, what can you do to avoid this effect, for example? And one thing we thought about is to try and include some kind of constraints into the adaptation. Use more information from about the impulse responses or about your environment to try and stop this misconvergence. Of course, one obvious thing to do is that if you have one known tap in your impulse response, you try and enforce the algorithm to always keep that tap the same. And one tap you could use is the direct path component. So the direct path of the impulse response, which you could say estimate with another algorithm for time delay of arrival estimation. So this is one way to do it. Another observation that we had is that this misconverged solution has some strange low-pass effect. It always tends to this low-pass tilted spectrum. And what we thought of doing is to impose a constraint that your spectrum should have somewhat uniform energy distribution across all frequencies. It's a debatable assumption whether this is the case, but I guess some parts of room acoustics support that idea that you have uniform distribution. Either way, whatever constraint you take, you can it just adds this. You can put it as a Lagrange multiplier, and it just essentially adds this penalty term into the adaptation process. And here's just one example of, again, quite short. These are shortened room impulse responses, simulated such. There are 5 channels, so each bit here represents one channel of the true ones. The room impulse responses are just truncated to 128 taps. Here is the misconverged solution, which also...
What's the sampling rate?
The sampling rate is 8 kilohertz here. So it's quite heavily truncated. It's mainly the initial parts of the impulse response. So here you have the misconverged solution using just the standard time domain adaptive algorithm. And if you impose the spectral constraint, you actually manage to stabilize it, although you delay the convergence a little bit. And the same effect you can actually see with the direct path component substitution. They both work in the same way. And here you can see the estimated channels, which sort of correspond quite well to the original ones. Another thing to do to try and improve things with adaptive filter is to try and get some kind of control of the step size rather than having a fixed one. And this is what another bit we looked at. So we tried to get a step size called optimal. And it's optimal in the sense that you want the step size to minimize the error between the true solution and your estimate at the next step, given your current estimate of the impulse response. And following this, you obtain a step size which at each iteration can be calculated using this. Now this contains 2 terms. One is this bit here, which has the gradient and your channel estimate, which is fine. This is available to you, so you can calculate it. But then you have this gamma term, which depends on the true channel estimate. So of course, it defeats the point a little bit if you need a true channel estimate to calculate it. If you look at the noise-free case to start with, this term is actually 0 because the true solution and the gradient will be orthogonal to each other at all points. So your optimal step size is fine. You can just get it by calculating from this bit. However, in noise, you don't have that. And what happens in noise is actually that this component. So sorry, just going back to the noise-free case, as you see that as the true solution, as the estimate comes close to the true solution, it drives the step size to 0, and it just stops the adaptations, which is what should happen. In the noisy case, this is what gamma does, is to help to support this driving of the optimal step size to 0. And we thought of trying to find some kind of approximation of this gamma term based on the bits that we have available. And yeah, so you can have some approximation of it. This is the one we used. And plug that in to the algorithm. So here I can show you just a couple of examples of what happens. So first, one of the issues with the optimal step size which it comes across is that it avoids selecting a step size manually, which can be quite troublesome. So here you see that if you have a step size of 0.02, the algorithm goes crazy. If you have 0.01, it's fine, but it's kind of difficult to tweak it and so on. So if you have the optimal step size, it selects it fine and it just converges, no problems. And here also you see that the two lines that are overlapping, so whether you have this approximation of this gamma term or not, there's no benefit when there's no noise, which is okay. On this figure, so here you have the misalignment on the y-axis and the iterations on the x-axis. You see that if you introduce this approximation of the gamma term, you can actually gain some extra performance in the estimation compared to assuming that it's 0 all the time. And another interesting bit is that if you do use the true solution as a step size, you get some really, really good convergence, as you would expect. But I mean, it's not a useful thing, but it just gives you some kind of a performance limit of what you can get with this step size. So just to sum up this part of the talk is that generally this, when you have some measurement noise, you disrupt this cross-relation error, and your performance degrades with these algorithms. However, if you try and impose some constraints based on additional information that you have, you can increase robustness to noise quite a bit.
Just a question here. So when you say measurement noise, what exactly do you mean?
I mean,
non-correlated across the channels noise.
With measurement noise, it's just generally any noise. So it could come partly from your equipment that you have, or noise from other sources in the room.
But those noises are different.
Yeah,
because in the equipment noise, usually from the microphones, it's non-correlated across the channels.
Yeah.
And the external noise is correlated because it's still a valid noise source and the sound wave reaches the channel, the microphones in a certain order. Yeah,
yeah. So, I mean, here, everything I've looked at here is with non-correlated, uncorrelated noise, yeah, generally. Yeah, so if you have any other questions about this part before I proceed to the second bit. Okay, so I'll look at the other side of the issue, is the equalization. So let's assume that you have some kind of estimate of your room impulse response, H, and you want to design some equalizing filters so that you get, when you convolve your impulse responses with equalizer filters, you get an impulse which can be delayed or scaled version of a true impulse. And that's sort of the ideal equalization, I guess. As many of you know, probably there's quite a few practical problems with this. One is that room impulse responses are non-minimum phase, and so you can't just have a single channel stable causal inverse filter G. And the second problem is that H is normally several thousand taps long, which causes problems when you try and calculate the filters. A third problem is that you normally have errors in your estimates of H, as you could see from from the previous part. So it can distort the equalized signal if you design your equalizers based on inaccurate estimates. And finally, you have this quite large dynamic range of the room transfer function, so that equalizing it exactly could boost quite a lot of narrowband noise. So the one issue I'm going to look at here is the multi-channel least squares equalization. So instead of having one filter per channel equalizer, you can have a combination of filters which altogether equalize the signals and give you one output. And this is generally known as the MINT algorithm, which is just the least squares solution to a problem which you can form from this relation. And the good bits with this is that, first of all, it eliminates this non-minimum phase problem. So you can actually get perfect equalization. Of course, if you have no common zeros between the room transfer functions, so the transfer functions have to be different. And the problem with this, on the other hand, is that it's quite sensitive to these wrong estimates of the room impulse response. Some attempts to improve that were made with some good results, I guess, by introducing a regularization into the minimization here. I can just show you a couple of examples of what happens if you compare this perfect multi-channel equalization, or if you have an approximate single-channel least squares equalization. So you have some kind of magnitude distortion and phase distortion of the equalized output. I'll go through this a bit in more detail, these measures, later on. And you have the system mismatch along the x-axis. So here, the plot A on both sides is the exact equalization with two channels, whilst the B plot is approximate equalization with one filter. And as you see, if you have perfect estimates of your channels, you get perfect equalization. If not, you start to get quite bad performance of these exact equalizers, whilst this more approximate single channel one kind of degrades much more gracefully. Unfortunately, to get this, you need very large filters. And in this case, I've used 15 times the length of the impulse response filter for the single channel. So that's not ideal. And another interesting observation, which I think is if you look at the length, so if you vary the length of your filter and you equalize it again with the multi-channel and the single-channel equalizers, you see that the error actually grows with the length of the filter that you're trying to equalize, although you're keeping the misalignment the same. So you get more and more trouble. So the idea from this is actually that it's best to try and do some short filter equalization rather than these long impulse responses.
Yeah, Nikolai, what are the units on the y-axis? For magnitude deviation, is it in dB?
Sorry, it's not really in dB. It's kind of dB. I'll show you the expression a bit later on. Okay. But this is just to demonstrate that you get some problem with this. It's essentially just the deviation of the magnitude from its mean. That's what it's supposed to be. Yes, so to try and shorten things, one obvious thing to do is to try and go to subbands, which people do. So you have, this is a figure of the full band multi-channel case equalizers. You have the signal, some channels, the equalizers, and you sum those up and you get your equalized output. Now, if you want to do this in subbands, one way to look at it is this, which is somewhat a conceptual version, is that you plug in this into the subband structure. So you have the signal, and in each subband, you have the channel, equalizer, and the output. I know this is quite a messy figure, but I think it does explain what I'm trying to get to eventually. So, yeah, so it just changes the order a little bit. And this raises, like from this figure, there's a few things. So one is, how do you choose your filter bank? The second is, if you have only the full band estimates of your room impulse responses, for example, how do you relate those to these subband filters so that we can design these subband equalizers? So starting with the filter bank, the one we chose to use was this oversampled filter banks, and in particular generalized discrete Fourier transform structure. The reason I chose that is that partly it's fairly straightforward to implement fractional oversampling, and also there are some efficient versions implemented for this. And why we want the oversampling is that we can perform filtering in the subbands approximately by using only one filter per subband, rather than the need of cross filters, which you normally have to have otherwise. So there's two properties which are helpful for this. One is that in these filter banks you can suppress the aliasing in the subbands significantly, and also there's very little magnitude distortion, the output of the filter bank. And having that, you can relate your full band filter to the subband structure, where essentially what we want to do now, I want to find the relation between the full band transfer function and these subband filters. So I want the transfer function of this to be equal to the total transfer function of the filter bank, so that if you input a signal here, you get an output here, which has the same relation as these two. And one way to do it is there's some guys who use this approach, and you can arrive to a least squares version to approximate these filters, because they're not exact. But it's you get pretty good results in terms of the error between this signal and this signal by using this this decomposition. And the other major advantage is that your subband filters of the room transfer functions are now the length of the full band filter divided by your decimation ratio, which is what we wanted to get to. And if you now have these estimates, you can design your equalizing filters for each subband based on these subband equivalent filters. And you achieve the overall equalization by applying the filters to each subband and then reconstructing the equalized full band signal. And of course, since the impulse responses of the room transfer functions have reduced by a factor of n, the decimation, so do the equalizers. So let me show you just a couple of results with this approach for equalization. So for this example, we use the filter bank with 32 subbands, which are decimated by a factor of 24, and you have a 512 tap prototype filter for the design of the filter bank. We simulate the system mismatch by just adding some noise to the impulse responses that we're trying to equalize, so that you get some desired misalignment. And these are the two measures that I had previously also, is the magnitude deviation and the linear phase deviation. So this is the two things we measure separately. So the magnitude deviation is, as I said, is the deviation of the equalized signal's magnitude from its mean, whilst the phase deviation is the deviation of the equalized signal's phase from a linear phase. So in the first case, this is just many randomly generated channels with taps randomly generated. The channels are 512 tap long, and it's 5 different channels. So you can see here the magnitude deviation on the y-axis, phase deviation on the y-axis down here, and it's system mismatch across the x-axis. So for the full band multi-channel LS equalization, you get what we got before, pretty bad distortion as you start getting inaccuracies in your estimates. Whilst with the subband case, you get a much more graceful degradation again, now when the filters are much shorter. And here is a case with longer impulse responses. So these are simulated room impulse responses of 4,800 taps. Again, there's 5 microphones. And the results averaged over 10 different locations of this source and the microphones. So you get pretty similar performances for the random channels before. And another nice thing with, so this, yeah, I'll just show you a couple of examples with this one case when you're here and one case when you're here, so that you can see what the output looks like. So here is the impulse response of the output at nearly with noise-free estimates of your impulse responses. And here is the magnitude. So you can see that it's pretty well equalized. On the other hand, when you have the minus 10 dB misalignment, you start to get some rubbish in the equalized output. However, if you listen to it, it doesn't distort the signal, which is quite interesting. With this, it just changes the spectrum, as you can see from this, but it doesn't distort it. So I do have some samples. I'm not playing any samples here because generally with reverberation playing through the room, it doesn't really get across the effect. But I have some samples on the computer. If anybody wants to listen with headphones later on, you can listen to what these things sound like. And another good benefit from this subband equalizer is that you can actually achieve quite a lot of savings in computations. So this is floating point operations versus your impulse response length, and it's somewhat consistent. So you get a factor of 120 reduction in computational complexity. So that allows you to invert the quite long room impulse responses fairly easily. And again, to just summarize this bit of the talk is, I think the key points with this subband equalizer is that you get a more efficient version of an equalizer, and you can improve your robustness to noisy estimates of your impulse responses, and you can get quite near perfect equalization at mismatches of smaller than minus 40 dB. And also, I think I like this decomposition, the complex decomposition tool for relating the full band and the subband impulse responses as general studies for any subband development of equalizers or blind system identification. So just finally, I'll show you a couple of figures on applying this equalizer to speech signals and some results on the Dereverberation in terms of bark spectral distortion and segmental reverberant to speech to reverberation ratio. So I know that this is a debatable issue of choice of measurement for evaluating reverberation in signals, but this is what I used here. And here you have several plots. So the bottom one, so this is segmental signal to reverberant ratio versus various T60s. This is also using simulated room transfer functions with 8 microphones. So here at the bottom is the unprocessed reverberant signal. the first figure, the first plot is just a delay and some beamformer, what that would do. And then each of these plots is for 0 dB, minus 30, minus 60, and no exact estimates of your impulse responses. So you see that if you have your perfect estimates, you can get perfect reverberation, more or less, and with noise, you're still doing quite well with bad estimates of your impulse responses, at least in terms of signal similarity. So though the debatable issue with measurements is whether they represent the audible differences, I believe that when you have some kind of signal similarity which reaches points down to here, it probably sounds pretty good. And a similar thing you can get also with, in terms of bark spectral distortion. Again, here is the unprocessed signal. This is a beamformer, and down here are all the lines for the equalized signals.
So in this case, we can say that bark spectral distortion is more sensitive on the small improvements, while the segmental signal to reverberation ratio shows us when you have a higher improvements, at least as indicator of what we're doing. Because practically yours are down there,
yeah.
All of those.
Yeah. Well, yeah, and if you now can relate, I guess, the bark spectral more to the audible difference, it probably shows that the audible difference between these three is not huge. That although you may have slight difference, so the point is that going from 15 dB to 30 probably doesn't make a huge difference when you listen to it, which I think can be true to some extent. So just to sum up the overall talk this far, I think is that this adaptive system identification and equalization, followed by equalization, can provide really good dereverberation in theory, which is good to have some kind of, that it's possible to do. However, in practice, it's difficult because you have a lot of noise and other issues, so it takes quite a bit of tweaking to get things working. However, I believe, and I think that was what I tried to get across, is that if you try and collect as much information about the environment and put it in as constraints to the algorithm, you can gain quite a lot of robustness and try and sort of reduce the blindness of the problem. And also the other bit is to try and reduce the dimensionality of the problem by divide and conquer approaches. And this hopefully will lead to some more practical algorithms using this type of approaches. And just before finishing off, I would like to thank a few of the people I've had the pleasure to meet and work with in relation to all this. And in particular, a mention to Patrick Naylor, who was my PhD supervisor and continues to be my support in things that I do. So thank you for listening. Thank you for your attention.
Questions, please. So, Nick Garbage has a meeting with most of you actually this afternoon. If there are no more questions, we can take a break because at 12 actually starts another digital signal processing talk here, which is organized by Dine. In this case, you will hear 3 persons from Advanced Signal Processing Center. And from my understanding, the audience will be the same, so we can take a break of 30 minutes and be back here again at 12. Thank you for stopping by. Thank you, Nikolai.
Thank you. Thanks.